Okay, so very briefly, everybody says this person does not need introduction, but they introduce him anyway. I'm not going to do this. I'm just going to say Yoshua Bengio, please. Welcome.
Thanks. All right, so today I'll talk to you about safety of AI and some inspiration from cognitive science to think about this problem. The first part of my presentation, I'll talk to you as citizens and our scientists who may or may not be experts in AI, about why we need to think of radical changes in our society and risks as we move forward towards human-level intelligence. And then the second part of my presentation will be more technical, talking about, what can we do to change the way we're designing AI systems so that they'll be safer and not harm people. Okay, so just as an important kind of starting point, let me remind you of the precautionary principle. I'm just reading from Wikipedia. A broad epistemological, philosophical, and legal approach to innovations with potential for causing harm. Little parenthesis, there's now a lot of research and also polls and a report, scientific international panel that I've been chairing, all sorts of reasons to think that there's a potential for causing harm. There's short-term harm that we already know about, and there's long-term harm that is harder to characterize, but there's that. Continuing the definition, potential for causing harm when extensive scientific knowledge on the matter is lacking. And when we talk about the future harm and the impact on society, this is clearly the case. And then Wikipedia continues, it emphasizes caution, pausing, and review before leaping into new innovations that may prove disastrous. So I'm going to claim that we're not applying currently. We're not on a trajectory to apply the precautionary principle. In fact, it's the opposite. We're like racing ahead with the leading AI labs stating very clearly that they want to reach human-level performance, or they call it AGI, and even beyond, like super intelligent machines. That's the roadmap. And some people in these companies are saying it might be as quick as just a few years. Usually academics think, oh no, that's crazy, it's going to be decades. But whatever it is, there's a good chance it's coming at us. And well, the image I like to use to illustrate this is, it's like humanity is like in this bus driven by a few CEOs. And we're getting into this mountain road where there's very little visibility. In fact, worse than that, there's a huge fog, so we don't see around each turn if there may be a precipice on the other side. And the scientists in the bus are saying, different things. Some people are saying, no, it's going to be nice, and don't worry, and we'll figure out how to brake when we get there, if needed. And other scientists are saying, no, wait, we don't know what is behind, we should be cautious. And some people think that it's going to be terrible, and some people think it's going to be so great, the world is going to be utopia. So there's like incredible divergence. But really, we are in the bus, and we're continuing to race ahead, at least with the current social construct with companies driving wheel. Companies and academics are working on ways to try to understand those risks, but for now, it's not very reassuring. So for example, there are safety protections in current large language models, but they are very easily bypassed. One of the problems that was discovered in ChatGPT took 12 months to find a patch, and they're all patches, like somebody finds a new attack every time they find a fix. There also is a lot of progress in how we can maybe control those risks with what's called capability evaluations. Like, does the AI have the capability of, say, helping a terrorist to build a particular kind of bomb? We can try to test for that, and that's what people are doing now. But these are spot checks. So what I mean is, we are asking questions to the AI to see if it can do some things. Like, by the way, one of the interesting ones is persuasion. And if we do find that the AI has the capability, then we know there's a problem and we try to find a mitigation. If we don't find it, it doesn't mean it's not there. It just means that our method didn't find it, which is sort of the wrong side of, you'd like to have a guarantee that the AI doesn't have the capability of doing something harmful, right? But anyways, that's what we have. And we do observe things like, systems that are trained with RLHF or variants having sycophancy. They want to please you, so they will lie in order to please you and deceive you in order to maximize their reward, which is not so surprising. Like, humans do that as well. There are even some mathematical arguments that I want to have time to talk about, showing that as you build systems that are better and better at maximizing their reward, the natural endpoint of this is that they would take control of the computer on which they're running so that they can give themselves maximum reward, which is just something you would also observe, by the way, in nature. If you allow animals to inject themselves pleasure, the difference is that here you wouldn't get just an addicted AI. You would get an AI that keeps its mental abilities and wants to make sure it's going to continue getting all this pleasure, and it will do whatever it has to do in order to prevent us from turning it off, for example. So these are, of course, theoretical arguments based on mathematical points, but there's so much uncertainty we don't really know, but we have to think through these things. So if you think about it, it's not just a technical problem, it's also a political and social problem, what people call social technical problem. And yes, we need to be better at building AI that by construction will be safe, that we can use it to advance our sciences and society, but that will not, even in the wrong hands, do really bad things. But that isn't enough, because even if we know a way to put some safety guardrails around our AIs, somebody with access to the code could just remove those guardrails. In addition, they could use the power of the AI, and power which is increasing and eventually reaches human level or superhuman, and use it for their own benefit, grabbing power thanks to the AI. So people who already have power, either in government or in companies, might, when they have the chance, abuse that power. This is something we've seen, in history all over the place. Even if a small fraction of people would do these things, well, some of them might be elected in 2 weeks, so you never know. Okay, so I'm going to now shift to maybe a more technical part of my presentation and start talking about the question of not just building safer AI, but thinking about the question, can we get some sort of guarantees that if we build an AI system in a particular way, if we design it in a particular way, it's not going to harm people in all of the ways that we can think of. And there is a fundamental challenge here, which I encourage you to think about. Usually in machine learning, the way we do things, and what has been very successful for me in the last few decades and the whole community, is have an intuition about, oh, we could have the AI be stronger at X by trying this, and then changing the algorithm or the way that whatever we do with the data and so on, and then try it out and see if it works. Okay, and usually it doesn't work. Sometimes it barely works, and then we get a paper. And sometimes it works, incredibly well, and you get a Turing Award. But that isn't good for the scenario where the AI could do something terrible, right? I mean, with humans around, of course, doing bad things. Why do I say that? Because the way we test that our AI is doing well, even from the point of view of safety, is we have a kind of test set, right? And we measure the average error or something, the average behavior according to some metrics. But if you think about catastrophic events, the average is not satisfactory, right? So maybe the average person is behaving well, right, on this planet. But a few crazies, 1 in a billion, is sufficient to, Putin or something, is sufficient to create a lot of damage. So we would like to have stronger guarantees, right? And so the usual way that we get guarantees, like probabilistic guarantees and so on, in statistics and machine learning, may not be appropriate. The other sort of insight here is that you might think it's impossible to get any kind of such like point-wise guarantees. And maybe it is, but I think we can move in that direction. And maybe to encourage you, think about the fact that mathematical theorems will remain true, whatever. Like even if we build superhuman AI that is able to do things that we can't conceive one day, math remains math, right? So if something is true and proven, it's going to remain true. So if we can have theorems that say, this can't happen, or it can't happen with some notion of probability that's sufficiently satisfying, then this is a guarantee that continues holding, even if we are faced with something that we have trouble understanding, maybe smarter than us. Okay, so now I'm going to zoom in on a particular way to try to achieve those goals. And so I'm going to also assume that we're going to build on top of the current state-of-the-art in machine learning, which is neural nets, but also thinking about maybe some ways of training those neural nets so that they can be more amenable to giving us the kind of probabilistic guarantees that I've been talking about. And for this, I'm going to introduce a notion of Bayesian oracle. So what is a Bayesian oracle? It's just imagine a neural net that somehow has been trained so that it can predict answers to questions or the probability of answers to given questions, given this data set, where these probability estimates are as accurate as they can be. And I'll come back to that notion, I think, in a couple of slides. Yes. Okay, so if we were able to estimate conditional probabilities, I'm going to claim that we can do useful things for them. I mean, the obvious one is we could predict the probability that, given a particular query or a query and an answer, a candidate answer, there will be bad consequences for people and so on. So, in principle, we could just predict those things. And then we can use that at runtime. So what do I mean here? Like usually the risk assessment that people are thinking about right now for LLMs and other AI systems is not at runtime. It is, once the system is trained, we ask it a bunch of questions. Maybe we try to fine tune it to see if it's able to do bad things. And then, we give it a certificate of safety. But we can't ever test every possible input or every possible query, right? And so we're never going to be very sure. But if we can have a runtime risk assessment, then, well, we don't need to check every query, just the ones that are being asked to the AI, right? So that's kind of reassuring. So I'm proposing to focus on this question, like given a particular context in which the AI is going to be used, or say a query or whatever, maybe goals that the user has, eventually we're going to build these agents. Like right now we're not very good with agency, but that's where the companies are going. And maybe a candidate action that the agent proposes to do in answer to the goal or the question. Use our Bayesian oracle to predict the probability that something bad of various kinds could happen. So how do we estimate these probabilities? So there's like basically two routes that my group is working on. One is sort of the short-term thing, which is we take LLMs and we try to convert them from estimating probabilities over sequences of words, which is nice but isn't quite what we want, into machines that can estimate probabilities for events, like logical statements, like the probability that somebody could use my answer. So the statement might be, the user might use this information to build a biological weapon, okay, let's say. So how do we go from a machine that predicts probability to a machine that predicts logical statements? So this is an open question. There's already a few papers trying to look at that. But one idea is you could use forced choice questions, right? So you could basically ask it, given this question and this future event, respond true or false to indicate whether this will happen or not. And so now the only words that the LLM is allowed to use, of course, it can do other things, but it's actually pretty good at forced choice questions because a lot of the exams are like that. So we know what the answers could be, true or false, let's say, because we asked it. And then we just ask the LLM to compute the probability of the answer true and the probability of the answer false. And there are complications, but that's one of the things that can be done. The other approach is more complicated and like rethink how we train them so we can get accurate Bayesian oracles. And I say a few more words about that later. Okay. Yeah, there's something interesting about estimating a Bayesian oracle. So as I said, like P of Y given X given data, and YX are any kind of events in the world. Contexts in X and possible things that could be happening in the future in Y. And if you think about the task is getting those probabilities, and you have chosen a fairly agnostic prior, then there's a unique and deterministic answer that exists. In other words, the Bayesian posterior is well defined. If you had infinite compute power, there is some calculation you could do, for example, using MCMC, but also other methods, that would give you exactly the right probability. The problem is that it's intractable to do those calculations. But that's where neural nets come in, right? So you can define objective functions, and we've already done things like this in recent years, that have the property that when you minimize the objective function, in other words, you find the weights of the neural net that make the loss 0, and the 0 is the global minimum, then you found the unique answer to how do I compute these probabilities. Now in practice, of course, it's not going to be 0, but at least you have this notion that there's no aleatoric uncertainty. Like the thing you're trying to compute is deterministic. The probability is not a random variable, right? It's a thing that's well defined. And also there's no epistemic uncertainty because I'm not asking the question, what would happen if I had more data? I'm asking the question about this particular quantity that is hard to compute, but then the advantage of this is I get guarantees of the form if the amount of data, not the amount of data, if the amount of compute went to infinity, which, future engineers will figure out how we approach infinity. But that's where we are. Like basically, we are currently on an exponential scale to make these machines bigger, as Irina was saying. So as we make our neural nets bigger and we train it for longer, we approach the correct answer for these probabilities. And that's kind of cool and useful. Okay, now the main thing I want to talk about is how do we avoid having these estimated probabilities being confidently wrong? And that's like the worst thing you can have in terms of safety, right? So if the AI says, oh, it's going to be all right, like the probability of something bad happening is 0.0001, then you say, yeah, let's do that. But if it was wrong, and you know, then we would be in trouble, and it just needs to be wrong once, right, on something that has terrible consequences. So just looking, so first of all, we shouldn't be using maximum likelihood in reinforcement learning because, I mean, standard reinforcement learning, because these would be happy to be confidently wrong in the sense that if there are multiple answers, like multiple neural net weights that fit the training set, then you can get any of them, and yeah, you know, the one you pick might be right in some cases and confidently wrong in other cases. Whereas the Bayesian posterior doesn't have that property. Basically, it would have to account for all the ways that you can make those predictions. And so it would be much more conservative. But even with the Bayesian posterior, there's a problem, right? Which is the Bayesian posterior is just an average over all the scenarios or theories that could explain the answer, like all the ways that a bad thing can happen in the future. And this average could hide something really bad that's unlikely. So what do I mean? Let me give you a concrete example. Imagine you had a committee of wise humans and you asked them the question, you know, is this behavior going to be harmful, right? And there were 100 of them. And 99 of them said, it's going to be fine. And one of them says, no, it's going to be terrible and, you know, 1 million people will die. The problem is when you look at the average answer from the committee, which is what you get when you ask the question, probability of harm given query and data, you might not see that bad thing, right? It's going to be diluted in the majority answer, right? Now, if you know something about democracy, you know, we have a notion of individual rights and we have a notion of diversity and so on. Why do we have that? Because just the average sort of vote might be hiding something terrible happening to just a few people, right? So what could we do? Well, instead of just looking at the average answer, could we find the guy in the committee, or the girl, who thinks that something bad will happen? And then actually we would like to find many of them and see how much of the total mass of probability they occupy. I mean, if it's 1 in a million, maybe, you know, that's some risk that you're willing to take. But if it's 1 in 100 and we're talking about, you know, millions of people dying, that's not good. So, so that's the project that we've started, and here's the math which you can't understand. But what it says is, so T here is like a member of the committee. T for theory, or you can think of scenarios. So there's a paper online called Can a Bayesian Oracle Prevent Harm from an Agent, which goes into this. And the idea is, let's look for a member of the committee, so here T is like a theory, that both predicts bad things. So given that scenario or that theory, the probability of harm will be high, and that theory has a high probability, P of T given the data. And then we can use this to upper bound the risks, upper bound the probability that in the real world, something bad will happen. We have a new version, the details don't matter that much. One problem with that paper is that this theory is something that we can't even like compute. Like it's a theory of everything, like how the world works, and you know that T would be as big as like you know, one of our state-of-the-art AIs, which doesn't make any sense. Like we can't sample 1 billion weights, right? It's just not going to happen, right? So we've come up with a new version where instead of having to sample, and that's inspired by you know, human cognition. Instead of having to generate a full theory of everything and see is there a theory of everything that's plausible and predicts bad things, we can just find a story, like something that's like a paragraph, right? Can we generate a paragraph such that the probability of that paragraph is high, so that's P, the phi here is like the story or the scenario, and the risk associated with the probability that bad things would happen is large. Here we're saying, it's above a threshold. And so we can use methods in modern probabilistic inference methods to try to get at this. So that, doing this maximization at runtime would be too expensive again, but we can approximate it. So we can train a neural net that will generate stories that would have both a high probability given the context and predict a high risk, right? So that's the sort of thing we're working on. Yeah, and there are a number of papers that my group has been working on that build on G-flow nets, which is something we invented 3 years ago, to do this kind of runtime optimization in a way that's going to be efficient. Yeah, I'm not going to go into these details. There are other questions that are related to this. So the first order question is to get these probabilities and use them directly to estimate these tail risks. Like, is there a story under which things go bad? Is the story plausible? And so on. But there's another problem, like a second order problem, which is we use this neural net that estimates these probability for bad things happening under different scenarios. What if the neural net is wrong? Because, okay, it's just a neural net. It's not perfect. We haven't got the error to 0, right? So when we train this probability estimator. So how do we estimate the reliability of that neural net, right? So, it estimates probabilities, but what we really want, because we want to be conservative here, right? We want to obtain guarantees, and so even probabilistic guarantees, right? We do need to have a sort of confidence interval around the probabilities that the neural net is predicting. There's already, again, like there's work in machine learning in what's called calibration and conformal mappings and stuff that we can probably leverage to obtain a distribution over the probabilities estimated by our neural net, and then use that to be even more conservative, taking into account the fact that the neural net itself is imperfect. The last thing I want to mention is the trustworthiness of these AIs that we're going to be building. So there's a fundamental problem that was, let's say, I don't know, discovered, but at least really studied carefully a few years ago. There's a 2022 paper, but I think the discussion, there's an earlier discussion on what's called the ELK challenge. So ELK stands for eliciting latent knowledge. And I'm going to use two settings. Like if you think about texts, you train the element text, but there are also maybe images. In the paper, they think about this picture where there's an AI and it sees images of what's going on in a room. In the room, there's a diamond, and you'd like to be able to ask the question to the AI: is the diamond still there? The problem, but is that you can't ask that question. The only thing you can ask is, in the image in the camera, do you detect a diamond? But somebody could have put a fake, picture in front of the camera, and so the AI would truthfully say, there is, I don't see an image I don't see a diamond in the image, or I do see a diamond in the image, even though like a thief has taken the diamond, right? And the problem is, usually when we do machine learning, the questions that when we estimate probabilities, the y's and the x, the inputs and the output kind of statements there, or variables, there are variables we need to observe in the data. But we don't observe these abstract things, and we don't observe things like harm. Harm is a latent variable. It's not something we directly observe. It's something that people report. The problem is, in text, we have the same problem. If you look at the text on which LLMs are trained, well, there's like a bunch of people lying or misguided, right? And so you can't really say that what you read is true. So if you ask, is this going to cause harm? Well, some people might have, might say that. Maybe there's a high probability that somebody would say there's no harm, but maybe they have intentions, right? I guess I have a cute example here. For example, some person X has financial interests in AI big tech, and that's a latent variable. Maybe I don't observe that. And we know that that causes X to lobby against AI regulation. This is a real thing that I've been involved in. I see that happening. And so that person might say, AI regulation would be terrible for society. And, whether it's true or not is going to be biased by the context of that person. But these are latent variables, right? And so the research challenge is, how do we ask questions in a way that the AI can't deceive us? It's going to be truthful. And we don't have answers for that. So these are some of the things that we're working on. And I'm going to stop here because my timer says 30 minutes. Thank you.